Now, a lot of you have heard of the term ideal model. An ideal model is not only noticed in all areas of science, but in this video, we're going to dive specifically into how it applies to the subject physics. And this involves what? This involves a replica of something small and how this is applicable to what you see around you. Like, for example, we know of things like articles or clothing displays, and all these are examples of what we are talking about when it comes to a model, and how a model is going to be applied to physics is going to be based on what? It's going to be based on how we need to be able to recognize the following, and this includes, first, we need to recognize that in a physical system, and this physical system can be any scenario that you might come across, either in terms of various problem solving or illustrations or experiments, and this here could be indeed fully complex in terms of how the questions are explained or delivered to you, and making this fully complicated, detailed expression or explanation or details of that scenario, and what? Doing something about it. We are going to be turning it into what? We're going to be turning this into a simple version of that particular complicated details is truly the goal of this particular scenario. And this simple scenario or simple version actually ties back properly to the physical system. And so how is this going to look like as we move into this next stage of this particular model that we are creating? Looking at an example like throwing a particular ball, and this ball in this illustration here is a tennis ball, because yes, I love tennis. But yeah, this shows a couple of things that may impact this particular ball if you consider everything. Like, for example, the ball as it's thrown is not a perfect sphere, and in terms of the shape, that means that it is changing. Another one is if you consider top spin or back spin of the ball, if you consider air drag, if you consider the uneven weight balance, if you consider the attitude change, this shows a couple of things. This shows an hopeless situation where you not only are including the direction that the ball is going, including gravity, but also you're including a drag that is putting it back in the form of a air resistance, that is a friction that is affecting the ball's motion, and also considering spin. This shows that, hey, this is a hopeless situation in terms of solving the question, and being in that state is truly challenging and difficult when it comes to finding the answer to the question or solving the problem. The next question is this: how can we generate hope by solving a problem that looks complicated, like the one we talked about here, where we have to consider all these variables before addressing the question? This hope comes from the following. We need to remember that we have to simplify, like what we have here, our version coming from the detail that we generated. And to simplify, we need to take a look at all these variables and take out things that are not relevant to the overall theme of this projectile style of motion. And recognizing this includes the following. First, we'll have to eliminate something here. We need to eliminate one, the size of the object. We need to eliminate the shape of the object. We need to also eliminate the rotation of the object. Therefore, we are going to be heading towards something that looks like a type of particle that is known as a point-like particle. And this point-like particle will be something that looks like a dot right over here. And next here is we're going to be considering air drag in terms of elimination. So we're going to remove air drag from this problem. Once we eliminate the air drag from this problem, we are going to consider what? This to be performed in a vacuum. And then next is considering this, eliminating the uneven weight. And considering this implies that we are going to do what? Attempt to consider that this particular object has a constant weight distribution that is around 8. Therefore, this will only take into account a couple of vectors, which is the direction of its motion and finally the force of gravity acting on it. This here is what we are expected to take note when it comes to creating an ideal model for a particular scenario. Now, one thing we have to remember is the following. We have to not ignore the most essential things in terms of a question. And what do we mean by this? This implies that one is for this question that looks like this. Gravity should not be ignored in this scenario. Reason is because that if we ignore gravity, what do you think is going to happen to this particle right here? This particle will continue to go up out of space and will not come down. And so that is something that we need to take into account in terms of not ignoring. And when you're looking at a question, think of the essential, which is the second part that we're going to look at here. Essential variables that are critical for this particular question, and this here implies the following. This implies that the direction of motion should be taken into account, and also sometimes there are some cases where if this object is moving in a circular path, we need to not only look at one, the direction of the motion, but also we need to take into account the mass of the object and sometimes the radius of the path that this object is making. So those are things to keep in mind when it comes to questions that may come up from this particular scenario. Finally, for applications of these, we have a classic experiment that was done by a well-known scientist by the name of who? Galileo. And these scientists performed a prediction type of experiment that enabled him to predict what? This prediction was about what we know to be falling objects. And this falling object he compared was the following. He looked at one which is pretty much a heavier object, which is known to be called a cannonball, and while the other is what? A feather. And when you compare these two when it comes to the fall, we notice that feathers are really subjected to air drag way more than cannonball, and so that is why I have a check for cannonball. However, this doesn't really work well for feathers, and what he had to do was to do the following. Just one change that everyone recognized, which is something known as air drag, and by putting that condition into play, this simplified this model in terms of enabling it to prove that for falling objects, it doesn't matter the weight, they both experience the same acceleration due to gravity if we ignore air drag. And so this is something that is really critical in terms of thinking about ideal model in physics experiments, and how most of the questions you're going to come across will say this: you have to ignore something. You have to ignore known as what? Air drag, or when this experiment is done in a vacuum. So I hope you found this really informative. Please hit the comment down below. Let me hear your thoughts about the ideal model that we explored, the physical system, how this is applicable to throwing a ball, how to go from a hopeless situation where we have many variables to take into account to a more simplified system where we have a hopeful way of solving that problem by taking some variables into account, and how this cannot be ignored when it comes to specific critical variables, and finally how this applies to various classical experiments, like for example the Galileo prediction about falling objects. I hope you found this really informative. See you all on the next one. Stay smart as always and believe in yourselves.